Hello everyone, my name is Isan. I'm the fourth year PhD candidate from the University of North Carolina at Charlotte. Today I'm going to present our paper about classifying security vulnerabilities into cyber weaknesses through a novel neural network design and represent the importance of this classification for proactive cyber defense. Every day, million lines of codes are written to develop thousands of applications and softwares. These programming efforts are not perfect, and any mistake at any level of production can make the system vulnerable to cyber threats. In the context of cybersecurity, vulnerability is an instance of software weakness, defined as an unintended flaw, mistake, or bug in a software or an operating system. These vulnerabilities are the result of faulty design, programming and implementation error, and improper computer or security configuration. Some of these bugs get fixed by patches released by vendors, but those left unpatched may create security holes where cyber criminals can exploit and perform malicious activities and compromise the system accordingly. Software weaknesses are often discussed and defined in the context of the Common Weaknesses Enumeration, or CWEs. These CWEs are a community-developed list of common software security weaknesses maintained by MITRE. CWE is a hierarchically designed dictionary of software weaknesses for the purpose of understanding software flaws, their potential impacts, and identifying means to detect, fix, and prevent those shortcomings. On the other hand, common vulnerabilities and exposures, or CVEs, are a list of publicly disclosed security vulnerability reports, where every report is assigned by a unique ID. CVEs are brief and low-level descriptions representing the standard means for sharing cybersecurity vulnerabilities within a specific product. Basically, CWE is a dictionary of software vulnerabilities addressing the underlying flaws, while CVE is a set of known instances of a vulnerability exploited in a particular system. CWEs shares a number of important factors such as description, common consequences, potential mitigations or detection, and related attack patterns. While CVE is a vendor-specific low-level description, CWEs explains how a CVE can be exploited, representing the conditions and procedures, why a CVE is exploited by describing the cause, and what are the consequences of the exploitation as impacts. When the vulnerability patching is infeasible, the classification of CVE into CWE becomes extremely important because CWEs can provide the means to understand the CVE implications, find weakness level mitigation, and helps to characterize vulnerabilities to develop further fine-grained course of action defense. Let's take a look at one example. Given this CVE stating SQL injection vulnerability in the libpam pgsql library B4052 allows attackers to execute arbitrary SQL statement. We see it mentions execute arbitrary SQL statement as attack action, the library as a vendor-specific cyber object, and the SQL injection as the consequence of exploitation. However, this is not enough, and there is a need to extract higher-level information to specify the characteristic of the security threat and accordingly find potential mitigation techniques. To this end, let's take a look at these CVEs associated CWE89 that provides beyond the product level of knowledge about this SQL injection vulnerability. It states faulty neutralization of a special element as the cause of attack, modifying intended SQL command to answer how it is exploited, and mentions read and modify application data and bypass protection mechanism as the consequence. Obtaining these factors is closely associated with the paradigm of pinpointing applicable defense actions. In the meantime, CWE89 recommends several detection methods such as using database or web application scanners, or prevention methods such as environment hardening or output encoding. As I mentioned before, CWEs as non-disjoint classes are organized in a hierarchical structure as a tree to reflect the inheritance relationship in which every non-root CWE inherits the whole characteristic of its parents. This hierarchy is very important when the most fine-grained CWE is not available for one CVE. where we can leverage the characteristic of the lowest level available node and its potential parents to estimate the characteristic of a vulnerability roughly. For example, if the fine-grained SQL injection CWE for this CVE is not available or is not classified, we can leverage the closest available coarse-grained CWE in the path to approximate the characteristics, like injection. Our discussion shows the value of classifying CVEs to their corresponding CWEs. Thanks to the cybersecurity experts and engineers, a great manual effort has been made initially by both MITRE and NVD to classify some CVEs to one or more CWE classes. Considering the growing number of CVEs and the high labor cost of manual classification, MITRE successfully classified about 5% of the CVEs and then stopped the process. NVD increased the quantity of CVE classification by mapping about 85,000. Although MITRE classified a smaller number of CVEs compared with NVD, it covers a higher number of unique CWEs and performs hierarchical and more fine-grained classification. On the other hand, NVD classified more CVEs, but it took less number of CWEs into the account without addressing the hierarchy. Due to a different point of view and approach, MITRE and NVD classification conflicts most of the times, and it's not possible to neither compare nor combine their classification. In the meantime, there have been several good research efforts other than MITRE and NVD to analyze CVEs to enhance the searching process and to perform CVE categorization automatically. However, these approaches are limited, incomplete, and without considering the hierarchy. Therefore, to the best of our knowledge, no solution has been proposed for automated mapping from CVEs to CWEs yet, and we are the first to propose such a model. Finding an automatic way for CVE categorization is extremely important since traditional manual techniques are costly, ineffective, problematic, and not practical. Our objective is to build a tool that takes the CVE descriptions and provide the corresponding CWE ID. Creating such an automatic system is challenging. First, CWEs are organized in a hierarchical structure. CVEs can be categorized with multiple labels. In this case, each CVE instance can be classified into one or more interdependent CWEs that belongs to the same path. In addition, some CWE nodes in the hierarchy class can be accessed from more than one path in the CWE tree structure. Third, there is a semantic gap in and between the language of CVEs and CWEs that makes the feature extraction phase challenging. So performing an efficient semantic analysis is necessary in order to identify the connection between similar concepts used in the CVE and CWE context. Last but not least, a considerably small percentage but high quality classification CVEs are provided by MITRE. On the other hand, NVD delivers a higher percentage of CVE classifications, but it used a lower portion of CWEs. So there should be a trade-off to process small and imbalanced datasets and classify CVEs into the most fine-grained CWEs, along with exploring the entire nodes in the path. As you can see here, our work to build an automatic system to classify CVEs to CWEs has 4 key contributions. 1. The development of first algorithm that automatically classifies CVEs to CWE classes. 2. A novel design of hierarchical neural network that is able to trace CWE classes to the most fine-grained in the CWE hierarchical structure. 3. A new approach to extract semantic and statistical features from CVE descriptions and compute the score that reflects the importance of the features in describing the vulnerabilities at each level in the CWE hierarchical structure. And 4. An adaptive learning technique that incorporates the computed feature scores by TF-IDF in a neural network framework to allow an automatic adjustment for feature scores to reduce the classification errors. Our proposed algorithm consists of 3 steps, including pre-processing, feature extraction, and hierarchical neural network decision-making process. The preprocessing component extracts the text from the description of input CVE instance and cleans it to generate a normalized version of it. First, it converts every word to lowercase, and then it removes so-called stop words to reduce the noise and feature space dimension. In the next step, it removes punctuations and special characters that do not convey important information. Then it performs stemming to reduce each word to its root in order to identify the relationship and commonalities across large text documents. Synonym word coding is the last step of preprocessing. It groups the synonym words in the context, assigns a code word to represent each group, and replaces all the synonym words with the code word which represent that group of synonym words in the context. These words are manually extracted from the alternative word section in CWEs and the CWE glossary which is provided by MITRE. This synonym vector coding helps in reducing the variance within documents in the same category and in increasing the distance between different categories. In the feature extraction component, the normalized text is processed to extract features to characterize the statistical and semantic properties. To this end, the input text is analyzed to generate a list of unique unigrams, bigrams, and trigram terms. The window size n in n-gram analysis is a hyperparameter and set experimentally. We tend to set this value to 1, 2, and 3 to satisfy stability and to avoid overfitting, since longer n-grams dramatically increase the number of word combinations that are rarely found in CVE instances and may cause overfitting in the training process. According to power law distribution, we remove the n-grams with the frequency less than 3 from the feature space. The remaining unique n-grams get a unique index to generate the dictionary as feature space. In order to generate the feature vectors for each entry, we create a vector of size d-1, which equals to the size of dictionary. The initial value of each element in this vector is 0. Then we extract the n-grams from each CVE descriptions, and then we look for their index in the dictionary. If the n-gram exists in the dictionary, we assign 1 to the corresponding vector item. Hierarchical decision making is a third step in the CVE classification algorithm. This step takes the feature vectors computed through the previous component and estimates the CWE classes associated with the CVE instance of interest. It follows a top-down approach by training a classifier per node in the CWE tree. For each node, a decision is made using the classifier that either leads down to a different classification node or to the leaf. This hierarchical architecture allows each classifier to focus on learning two aspects of its children: the details that distinguish between the classes of its children, and learning the common features between the classes forming each child. This approach helps to simplify the design of this classifier to reduce the computational cost, as well as improving the accuracy of the system by making each classifier to focus on its children without getting confused with the other nodes. In the classification procedure, for each node, the neural network takes the feature vector and predicts the label of the class in the next level of the tree. In this case, the neural network starts to classify CVEs to CWEs that exist at level 1. In the next level, the neural network finds the predicted CWE classes in the previous level and takes their children for the next level of classification. Each neural network consists of one hidden layer. The number of neurons in the hidden layer equals to the number of classes present at the level L in the CWE tree. Each neuron is fully connected to the input feature vector. The sigmoid function in every output neuron generates a probability score. If this value is higher than an imposed threshold, it means the input feature vector belongs to the class associated with that neuron with the high probability score. Instead of randomly initializing the weights, we set the TF-IDF score of each engram in feature space with each class. This score shows the importance of that engram feature for each class at each level. So if a feature is a key signature of one class, the connection weight will be high, which will help the neural network to predict the correct class. This simple neural network has been employed for three main reasons. First, to reduce the computational cost by reducing the number of variables that a neural network needs to learn. Second, to avoid the overfitting problem, especially when the size of the training dataset is small. And third, to allow mimicking expert thinking process when classifying CVEs to CWEs according to the terms mentioned in the description and their knowledge about the CWE classes. A comparative evaluation experiment have been conducted to evaluate the performance of ThreatZoom on the labeled CVE sets provided by MITRE and NVD. The evaluation compares the estimated CWE candidate list generated for each vulnerability in two different levels, including coarse grain and fine grain. To be more precise, if the model predicts one or a sequence of CWE classes which are not necessarily full path toward the leaf, it is considered as coarse grain classification. On the other hand, fine grain classification happens when it successfully predicts the full path to the leaf, where here the leaf means the labels in the ground truth. Our model successfully results 92% and 94% accuracy in fine grain coarse grain classification over NVD set. In addition, it shows 75% and 90% classification accuracy in MITRE dataset. Although there is a 17% gap in accuracy of classification between NVD and MITRE, ThreatZoom shows it is able to learn short corpus and imbalanced data with the promising performance, and it can perform even better if it receives more training examples from the MITRE. In the second experiment, the hierarchical neural network framework is replaced by a regular flat one, such that the neural network considers all the class in one-shot classification process, regardless of their hierarchy, and initialize the weights randomly during the training process. In the third experiment, the single-layer neural network classifier is replaced by two-layer, and the neural network weights initialized randomly during the training process. The results show a significant difference in the performance of ThreatZoom and the other models. We also took one more step forward and tried to predict more fine-grained CWEs. Reported results show not only ThreatZoom perform as good as the MITRE and NVD engineers who are well trained for these tasks, but also it accumulates their experience to offer even more fine-grained CWEs. ThreatZoom obtains more fine-grained classification for about 47% and 95% of those CVEs that were correctly matched by MITRE and NVD respectively. To validate these results, we used our domain expertise to manually inspect 100 randomly selected CVEs that received fine-grained classification by our tool. This paper presents an automated technique for fine-grained classification of CVE instances to CWE classes. To this end, we discussed the existing challenges and shortcomings and introduced ThreatZoom as a novel blend of text mining techniques and neural networks to map security vulnerabilities to weaknesses. To the best of our knowledge, ThreatZoom is the first automated system that addresses existing challenges and limitations of classifying CVEs to CWEs. This tool is already being developed to leverage word embedding and deep neural network to better classify CVEs to CWEs following the MITRE standards, extract threat actions out of CTI reports, automatically calculate threat severity scores, and find the potential course of action mitigation and detections accordingly. Thank you, and I hope you enjoyed this presentation. Please let me know if you have any question.